The speed of sound. The so-called speed of sound is the rate of propagation of pressure pulse of infinitesimal strength through a still fluid. Let me write. Speed of sound is the rate of propagation of a pressure pulse of a strength through a steel flow. It is a thermodynamic properties of a fluid. Let us analyze it by first considering a pulse of a finite strength as shown in this picture. This figure, the part A, the pulse or pressure wave, moves at the speed of c as shown here. Toward the steel fluid. P, rho, T, V, and where V equals to 0 at the steel of fluid at the left as shown in this picture, leaving behind at the right a flow of increasing properties as shown here. Increasing properties at right T plus delta T and a fluid velocity delta V toward the left following the wave but much slower. We can determine these effects by making a control volume analysis across the wave to avoid the unsteady term that would be necessary in the A part of this picture. We adopt instead the control volume of the fixed wave at B. So we can write the continuity equation in the two sides of the steel of fluid. We have this relation rho A C should be equals to the right side of the steel. A is same for both, but the velocity and temperature is different. Now we can obtain C on this proves our contention that the induced fluid velocity on the right is much smaller than the wave speed c. Let me induce it. On the right is much smaller than the wave speed. C. In the limit of infinitesimal wave strength, this speed is itself infinitesimal. Notice that there are no velocity gradients on either side of the wave, therefore, even if fluid velocity viscosity is large, frictional effects are confined to the interior of the wave. Advanced texts show that the thickness of pressure waves in the gases in order to a small number in atmospheric, thus we can safely neglect friction and apply the one-dimensional momentum equation as this relation. V out minus V in. Or we can write for momentum rho m dot is equal to rho a c multiplies the two difference between two velocities, which are now at the end we can obtain delta p equals to rho c delta v. If the wave strength is very small, the pressure change is very small. If the wave the pressure change is small. Finally, we combining the equation in the previous sheet, this equation and the momentum equations that obtain this relation that obtain from momentum equation, we can obtain the relation between the speed of sound and the dynamic properties. The larger the strength of the wave, the faster the wave speed. That is, powerful explosion waves move much more quickly than sound waves. In the limit of infinitesimal strength, we have 10 to 0, and we can write the speed of sound A for a fluid as this relation: A squared but the evaluation of the derivative requires knowledge of thermodynamic process undergoes by the fluid as the wave process. We now see that the correct process must be adiabatic because there are no temperature gradient except inside the wave itself. Correct process must be adiabatic because there are no temperature gradients except inside the wave itself. For vanishing strange sound waves, we therefore have an infinitesimal adiabatic or isotropic process. The correct expression for the sound speed is isotropic for any fluid, gas or liquid, and when a solid has a sound speed at temperature and at the isotropic and temperature constant relations. For a perfect gas, we have relation for speed of sound as RT. The speed of sound increases as the square root of the absolute temperature. The speed of sound increases as the square root of the absolute temperature. For air with An easily memorized dimensional formula can be obtained, and we have for the as T is in Kelvin, and in the US customary or British units, foot on second. T in Kelvin, T in Rock. Table 1 provides various information about the speed of sound for different gases. Some representative value of sound speed in various materials are given in this table. For liquids and solid, it is common to define the bulk module K of the material. The bulk module value or bulk module equals to isotopic process. In terms of bulk module, we have the speed of sound also as a function of the bulk module is rho K in this equation is bulk modules at a standard condition. The bulk module of liquid carbon, for example, have different quantity. For solids, they sometimes assume that the bulk module is approximately equivalent to the Young module of elasticity, but the fact the ratio depends on Poisson ratio. The next section is adiabatic and isentropic steady flow.